Hello everyone, welcome back on the course of higher surveying, and we are in module 6 on photogrammetry. In the last lecture of this module, we discussed about a lot of scattered information which were very introductory in nature, and then we realized that what are the types of platforms, what are the types of photographs, and basic terms like aperture stop, focal length, focal plane, and so on. Now, from this lecture, we are going to be very specific for a particular aspect of photogrammetry. So today we are going to talk about vertical photogrammetry. So this is our lecture 2 on vertical photogrammetry. If you remember, or if you can recall the last lecture, we talked about different types of photographs: vertical photograph, tilted photograph, and oblique photograph. For a photograph, if optical axis matches with another line or gravity line or plumb line of camera, then we say that it is a vertical photograph. If optical axis is tilted within 3 degrees from the another line, we say it tilted photograph. And if tilt is more than 3 degree, it is oblique photograph. We will not go in for bifurcation further, but we will try to understand the small nitty-gritties of these aspects today. Also, we are going to understand technically how we can make map using these photographs, especially the vertical photograph and tilted photograph. So let us go ahead. These are the books. First 3 books are sufficient for this lecture. What is field of view? In case of vertical photogrammetry, camera is mounted in aircraft or helicopter. This is flying direction. So this is what we call a pixel, which is shown by a black color pixel on ground, not on the sensor. On the sensor we call one unit as pixel, but when it acquires some area on the ground surface, then we call the size of pixel as ground sampling distance, or GSD. Secondly, I am talking about the digital cameras because they are the only popular one now. All the film based cameras are obsolete. So we are going to talk about a digital camera in the photogrammetry. So we have a digital aerial camera mounted in aircraft, and that is acquiring one scene, and this scene is explained by these pixels. So it is a frame camera, so it is making one exposure and acquiring this scene. So in this scene, so many pixels are there, and one pixel size on the ground is called GSD, ground sampling distance. This angle, which is along the direction of flight, theta y, this angle is field of view along track, and that is flying direction. Similarly, we have another field of view which is called field of view across the track or across the flying direction or on the sensor. So this is the angle. So each of the pixel is subscribing an angle on the camera perspective center. The angle subscribed by the one GSD or one pixel on ground is called instantaneous field of view or I of OV. This distance, which is across the flying direction, is called swath or swath width. Both names are popular, both are the same. You can see that the instantaneous field of view in x direction can be calculated by FOV in x direction, or theta x, divided by number of pixels in x direction. Like this. Let us say the number of pixels is equal to nx. So then I can write that the IFOV x equals to theta x divided by nx. So I can say here that these number of pixels are equal to nx number. Similarly, if number of pixels here from 1 to, let us say, this number is ny, so I can write I of OV y is equal to theta y, or the FOV in y direction, divided by number of pixels in y direction. One should note here that in general the pixel size on the sensor is same for x and y direction. That means we have square size of the pixel. That is why the FOV and number of pixels in certain direction x or y, they are decided or designed according to this criteria, so that we will have square size of the pixel on sensor, as well as that square size of the pixel on sensor should create a square size of GSD or ground sampling distance on the ground. Let us discuss the vertical photograph now. In the previous slide, I assumed that camera optical axis and the nadir line or the gravity line are matching. What does it mean? So, let us say there is a terrain, this distance is a swath, this is camera assembly, this is flying height h, so this is negative image plane, and this is exposure center where all the rays from the terrain are going to meet and going to again diverge towards the image plane. This is the optical axis shown here. So, this is the focal length. So, this is the way all the rays are converging to the perspective center, and again they are diverging to the image plane, and they are creating an impression on the sensor or the image plane, or we can say negative plane. Now, negative and positives are no more valid term, but still we are going to use these in order to distinguish between a negative plane, that is a sensor plane, the positive plane which we really see, because as we know that negative plane image is an inverted image, and that is why we need a positive image. So, this is a positive image shown here, and which is also located at a distance focal length from perspective center. So, that is a mechanism of data acquisition for one exposure of frame camera. So, that is swath. What about this distance? This is also called swath, but swath along the flight direction. So, this is the swath across the flight direction, and generally we do not write across the flight direction. So, this is called swath, the whole term. So, whenever you want to specify this swath which is along direction, you have to specify like that. Okay. So, now I can write that swath is equal to 2h tangent of theta x by 2. So, that is negative image plane. This is perspective center or exposure station, this point. Originally we used to have negatives. So, once we develop negatives, then those negatives have 4 marks. So, these 4 marks are called fiducial marks, which are at the center of the edges of an rectangular image. So, if we connect them by straight lines, they will intersect at a point, and that point is called the fiducial center of the image. That means, if I draw the line through the fiducial marks which are opposite to each other, then I will find an intersection point, and that intersection point will be fiducial center. So, this is optical axis, and we can see here that fiducial mark and optical axis are not meeting at a common point, because I am assuming that although it is vertical photograph, but there is some random error in the optical axis, and as a result it is not matching with the fiducial center of the photograph. Yes, what about the random error? If you can recall the concepts of the adjustment computations and error accuracy, it is an inevitable error. It is random, it is beyond control, or I cannot measure it. I do not know its true value. So, its intersection point is slightly away to show that. This is the point where the negative image plane and the optical axis intersects. It is called principal point, or it is also written sometimes PP. Next is principal distance, that is the distance between the principal point and the exposure station along the optical axis, and that is the focal length. Now, that is positive image plane, which is just shown here. This is the fiducial center mark of image or photograph, or I can say there is a fiducial center on the negative plane. Same way, if I am marking the intersection of fiducial mark on the photograph as center of the positive image, then if I extend the optical axis down towards the positive image, it will interact somewhere here. So, this is principal point on the positive image plane. So, let us draw the x-axis and y-axis on photograph, so that I can refer any point on the positive image. This is the gravity direction. So, now you can see even the fiducial center of the image is not matching with the nadir point small n, which is a reflection or image of the real nadir point on the ground. So, we have realized that optical axis need not to match with the gravity direction, because there is a random error, and we know that there is a random error although we cannot measure it. Secondly, optical axis itself is not matching with the fiducial center of the negative image, but still optical axis, gravity line, they are passing through the exposure center, and exposure center is the point where all the rays from the object are coming and they are converging, and then again they are diverging towards the image plane. So, this point, let us say, is the projection of another point in positive image. So, now you can understand how are they different. So, let us talk about the vertical photograph and the scale. If you remember the scale of the map from the basic surveying, we define scale as the distance on the map to the corresponding distance on the ground surface. So, same concept is there, but now we are going to do for the photograph. Moreover, we are taking the vertical photograph. Third thing, we are assuming that our optical axis and the another line or the gravity line, they are matching exactly with each other. That means we are talking about the theoretical derivation. It is going to simplify work, and that is the reason we assume that there is no distortion in the optical axis or the principal point. So, principal point is matching with the fiducial center of the image. Let us see, there is a datum. We have a point A0, we have optical center O here, and this is the positive image, and small a0 is the image of point capital A0 in photograph. Let us say OK, this is optical axis here, and that is also matching with the gravity line or the plumb line passing through the exposure center O. The scale is the ratio of the distance on the photograph to the distance on the ground. That means, if I take 2 points on the photograph, then if I take the same points on the ground, and if I calculate 2 distances, and if I take the ratio of the 2 distances like this will be equal to the scale of the photograph. If you look at here, Ka0, this distance divided by K0 A0. Let us use simple mathematics of similar triangles. First is this triangle and second is this triangle. So, the bigger triangle is shown by blue color and the small triangle shown by the red color. So, what about scale? It is OK divided by OK0. The ratio of this distance, which is this, and this distance equal to the ratio of focal length and this flying height, this distance, and that is written here. So, scale of a vertical photograph is equal to the ratio of focal length to flying height. So, S is equal to F by H. Once again, we are talking about scale of a vertical photograph. Let us say there is a ground surface like this and there is a datum like this. That means, I am measuring flying height with respect to the datum. So, if you see that there is a point on the ground which is A, and on the datum its projection is A0. This is the A point, that is image of this point. So, this is optical axis, and then K point is principal point, or capital K point is the projection of the principal point on ground, and K0 is the projection of principal point on the datum. Ground has certainly some height. As you remember from basic surveying, we measure the height from datum, that there is a plane datum and I am measuring the height of point A. So, this is the height HA of point A with respect to datum, and as a result of that, what happens in the scale? So, I have the flying height H, and if you see here, flying height at point A above the ground, it is H minus HA. So, distance Ka is this distance, and distance on ground is Ka, which is from this point to this point, this distance. So, again use the similar triangles, but there is small difference in the scale expression now, because point A is above the datum at height HA. So, again use similar triangles. The scale is the ratio of F and distance from the exposure center to the point. So, this is the scale at point A. In general, for any point having H elevation, I will have the scale, and that is what we call the point scale, the scale at that particular point. So, at point A, I have this scale. A on ground. So, because HA is above the datum, so you will get better scale or higher scale on the photo. Similarly, what if the point A is below the datum? At that case, H is equal to F upon h minus of h, because this height h is measured below the datum, that is why I am putting minus h, and as a result I will get h plus h. So, if a point is below datum, I will get inferior scale or smaller scale, but if a point is above the datum, I will get the better scale or superior scale. Remember that we always measure the flying height with respect to the datum. So, here I am showing 2 points. So, at point A I have this scale and at point B I have this scale. I hope you are very much familiar now with the scale. So, let me define some different type of scale. First of all, a datum scale. If a point A is lying on the datum, that will be the scale here, and we call it SD, that is scale at datum. Okay, what if the point lies above the datum? This is going to be the scale, and that is called the point scale, because this varies from point to point. Okay, now as we know that terrain is always varying, because of that we will have different elevation at each point. So, each point will have a different scale, but as you know that map is always having a uniform scale. So, derive a term called average scale. Take the average value of the terrain elevation. Remember that average scale is not an absolute scale, because for each point scale will vary, but still in order to make a map I need to define an average scale, and that is why I am taking average elevation HAV from most of the points. So, this is a preferable scale when the variations on the ground surface, that means the height variation of different points, are in same order, right, and accordingly it will decide the scale. So, if the variations are very high, for example 200 meters, in that case this average scale will not carry any meaning, because one point definitely having very high scale which is on the top of a hill, and there is another point on the ground surface having very low scale. So, if I take the average, this average scale is not going to represent the real ground, and that will give me the map which will give me lot of errors. So, we should be very careful while we use any scale. So, let us talk about the displacement that are evident on the vertical photographs. So, first is a relief displacement. So, let us see there is a datum surface, and from datum surface if I measure the height HA and HB for 2 points A and B on the terrain, they are the elevation from the datum. Now, B0 is this point here, and similarly A0 is this point. So, there is an image and there is an exposure station, and so this is the optical axis which is pierced datum at K0, and principal point K here. If I extend the optical axis or the other line in the gravity direction, this is this point here. Height of the point K with respect to datum is HK. The point A here, it is imaged at A. Similarly, for point B is imaged at B here. Now, the image of point A0 which is at datum is imaged at A0 here. Similarly, this point is imaged at B0. So, you can see that because of the height of point, the image of the point shifted. That means, the point B if here at the B0, then it should create an image here, fine, as you can see, but the point B is at height HB above the datum. So, it is creating image at B, right. So, as a result I can see that the image of point B is shifted from B0 to B because of the height of the B or height of the location B with respect to datum, and I am still measuring the flying height above the datum, and as a result each and every point which is above the datum will shift in the photograph. So, you can see that if there is a building which is at ground surface, so its point on the ground surface will have different image than the top of the building. So, this point will be imaged somewhere in the photograph, and this point will be displaced because of this height, let us say h, and this displacement in the image of the point is called relief displacement. So, this is relief displacement here which is written here. Similarly, I have relief displacement BB0 for point B, this is this. So, now let us try to understand what is the concept again. So, let us say there is a tower, this is one triangle. So, this distance is r, this is this point A0 and this is point is A here, r and r0 are the radial distances from the principal point. If I draw the two similar triangles, so you can see here, so this distance is r and this distance also r. So, now I want to derive the relief displacement. This is R0 and R as marked here. So, this distance R equal to K0 A0. So, this is K0 here and this A0 here, which is bottom of the building or the tower. So, K0 A0 is radial distance R. If I take two triangle, the ratio of F to the flying height H minus H is equal to the R by R. R is small k A divided by K0 A0. So, I can write that radial distance R of point A from the principal point is equal to this R F into H minus H. Similarly, I can write from other triangle this relationship F upon H, that means the ratio of focal length to the complete height H, which is this height, equal to K A0 divided by K0 A0. And as a result, I can write from this equation that R0 is equal to Rf by H. Now, what is the displacement? The displacement of the image point is d, which is given by this. We are just doing simple subtraction. From there, I can write this expression. Further, I can say what's the value of R here. So, R is nothing but I can write like this, and then I can also write equal to this one, because from this term I am writing this term, and from here I am writing this term. As a result, if I replace here in the R, d is given by R into H minus H by F into this thing, finally this expression. You can measure R on the image, because you know if this is a tower, so this is the bottom of the tower here and this is the top of the tower. So, we see the image of the tower in the photograph. So, this is a point A and A0. So, this is R from here to here. Similarly, I know flying height and assume that I know the height of the point, or that is height of the tower, this, what's tower height above the ground surface. I can find out what should be the replacement of, or what is the shift in the image of the point. Similarly, I can also write this thing instead of putting this expression here in this equation. If you put this expression in this R, you will get this expression. So, that means even you measure the R0, which is the distance of the image point A0 from the principal point, and A0 is nothing but the image of the bottom of the tower or bottom of a building. You can measure what should be the displacement of the image of a point A because of its height above it, and that is what we call relief displacement on a vertical photograph. So, if you look at the characteristics, you can see that relief displacement increases with the increase in the distance from principal point. Principal point is not small k on the image. The relief displacement decreases with the increase in the flying height, because this is the expression we have H upon H minus H here. So, relief displacement of a point on the ground which is above datum is positive, as I already explained, and below datum is negative, and relief displacement decreases with the increase in the flying height. So, if I increase the flying height here, the relief displacement will be lower, right, and that is the key. If you do not want a relief displacement, increase the flying height. So, what will happen in that mission? All the buildings will appear small, but in other sense, relief displacement also gives some sense of height. So, choice is yours, whether you want to suppress the heights or whether you want to increase the heights represented in the photo. Secondly, if you can imagine now satellite at the height of 750 kilometers. In case of satellite, I will put this H is equal to 750 kilometers or 900 kilometers, whatever the height, and as a result, you will not find any relief displacement in case of satellite images. The satellite images are best source for the planning metric mapping. That means I want to do the XY mapping, not the 3D mapping. Why do we prefer the aerial photography or aerial photogrammetry compared to the satellite photogrammetry? The satellite photogrammetry will give me minimum vertical exaggeration. As a result, I cannot create a reliable 3D information maps using satellite photogrammetry. But in case of aerial photogrammetry, I will have relief displacement, and by some way, if I measure the height of the buildings or height of the terrain points with respect to datum, I can prepare the 3D map. Okay. The height of an object, let us look into this, can be determined by relief displacement, and let us see how. And I want to find out height of this point A. This height is H. So, let us see this image. I am making it again without going into detail, because we have already seen this thing. So, I can write H is equal to the height of the tower or building. I will measure this D. I know the flying height and R. So, this distance is R. This is R0 from here to here. So, I can find out from this formula what is the height of the point above the ground surface. and that's the advantage vertical photogrammetry, especially aerial photogrammetry, gives compared to the satellite photogrammetry. Now let us take tilted photograph. What's the meaning of tilted photograph? When we say that there is a vertical photograph, which means the gravity line is matching with the optical axis. Theoretically it is correct, but because of some random errors, we can assume that optical axis is not vertical or it is not matching with the gravity direction. Rather, it is slightly shifted in the photograph and it creates a principal point away from the fiducial center. Now imagine that there is a tilt. That means optical axis is tilted with respect to the nadir or the gravity direction. It is unintentional tilt, but still there is a tilt and I know there is a tilt. That means it is no more a random error. It is a kind of systematic error that I know. So tilted photograph, I am saying I know what is the tilt. Although it is unintentional, it is undesired, it is happening, but still I measure what is the amount of tilt. I know it beforehand. So let us look into that how scale is going to change. So let us see there is positive image plane. So this is the point N, which is the nadir point on the image. So this is optical axis and it is creating principal point K. So this line which joins the small n to K, it's called principal line. This angle is tilt, and if I draw a horizontal line in a horizontal plane like this, then you can understand that this angle is tilt here, T, this T and this T. They are same, but they are in different planes, they are appearing different in animation. So I am showing that this is tilt here with respect to horizontal, and there I am showing like this. So this is my optical axis by finger and the pen is showing the plumb line. So this is tilt angle here. So that is shown in the animation. Now if I bisect the tilt angle by a line as shown in the animation, it will intersect at point I, and this point I is called isocenter of image. So now we are trying to find out I also, and there is a reason for that, we will see. Now we have understood what is a tilted photograph. So in the books you will find this kind of photograph, right, where this is N point here and this is K point, and so this is the tilt angle, total tilt angle is this. So as a result this point is isocenter, which I will get as point I on the image. If I bisect tilt angle, let us measure the scale of the tilted photograph. So let us say this is a point A on the terrain, so there is a datum, point A has height HA. So let us say there is an image. So there is a point N and there is a point A here which is imaged. Now this is focal length F, this is optical axis. So line joining N and the point K here, it is principal line. So if I take point A and draw the perpendicular to the principal line, I will get point M, and similarly if I draw the line from point M to the vertical line or the gravity line, I will get M dash, right. Because of the tilt, I know that another point which was like this now has shifted from here to here. It is passing like that, so optical axis is like that, fine. So this focal length, this is another line here, right. So this kind of arrangement is there, and as a result, because this is focal length which is perpendicular to the tilted image, and now this one. So I know that this distance, which is little smaller than this distance, right, has to be taken for the scale calculation. So let us see this distance. If I take here up to M dash, then this distance divided by the flying height, which is this distance, this is scale in case of tilted photograph. So let us draw a triangle which is in the horizon plane. We are also drawing the same triangle in the ground surface, which is shown by NMA. So this is flying height H, this is the H minus HA. This triangle, that means O M dash A in the image, and this triangle capital O, capital N and capital A, they are similar triangles. So I can say M dash A divided by NA is scale of the tilted photograph. And as I told that M dash A is not measured along the nadir line here, but this distance is from this point to this horizontal plane, like this distance, fine. So this distance I am trying to measure and I am showing the ratio of this distance to the flying height, which is h minus ha, is scale for point A if point A is on the tilted photograph. So, now m dash A divided by n A, it is O m dash, again I am taking the same ratio by O n. So, O n is this distance, which is equal to h minus ha. Now, let us calculate the O m dash, which is slightly complicated because of its involved mathematics. O m dash, it is O n minus m dash n. So, O n is equal to the f sec t, where t is tilt angle and m dash n is equal to m n into sin t. So, you can use this triangle shown here. Let us go ahead. So, now coming to the O n, as I already told, O n is equal to h minus ha. So, I can write that sh, the scale of the tilted photograph, is equal to this ratio. So, this is this distance and this is this distance. So, this is the scale of tilted photograph. Still there is something to say here. Let us wait. If you go back to the photograph here, we have assumed that we are measuring these distances along the principal line. In fact, on a photograph, we do not measure anything on the principal line. It is just a concept. We measure with respect to fiducial center only and the axes which are parallel to the edges of the photograph. Let us draw this thing here. Let us say point A, and that is nk and m. So, this angle is theta. So, this is y dash and now x dash axis. So, I am measuring this point A here in the image coordinate system, what I call x y, but I know that I should measure this in the x dash y dash system, which is at angle theta, because I know if this is the principal line shown like this, its angle is theta here with respect to the y axis. So, I can write here that these are the desired coordinates y dash and x dash, because x dash is measured along this axis x dash and y dash is measured along the y dash axis here, and this is principal line. So, now I have to correlate image measurement x and y to x dash and y dash. This is y for this point and this is x for point A, and this is x dash from here to here and this is y dash. So, now by simple transformation, so I can write x dash and y dash equal to this, plus this term will also come because image plane is tilted. In the last slide, there was a term mn, which is equal to this distance y dash. So, I am putting the y dash here instead of mn, and y dash is given by this. Now, you can measure the scale on the tilted photograph also. Try it yourself, try to do some experiments with your mobile camera. Create some object, try to put tilted camera like this and capture image and try to calculate the tilted photograph scale. Also, try to calculate relief distortion. Let us say there is a building like this. So, put it on your table like this and then try to acquire the photograph like this and try to see how this point, the bottom of the pen and the top of the pen has shifted in the image. Because of the height of the pen, you will find out that there is this point has shifted in the image outwardly from the principal point. That is the idea here. Try to do these experiments yourself. Assume that mobile camera is mounted in an aircraft and your hand is an aircraft. So, now you are acquiring the photo of a certain terrain where this is a building. So, now if you take the photograph in which this is appearing, so you will find out the bottom and the top of the pen are appearing at different positions, and the difference from the center, which is I am assuming that center of the photograph is the principal point. So, if you take the radial distance from the center to the image of the bottom point and the image of the top point on the photograph, you will find out they are lying in a one line approximately, assuming that there are no distortions in the optical axis. So, radially they are outward. Similarly, you can do another experiment. Assume that there is some valley where this is your bottom point and this is a point below the bottom or below the datum. So, you can find out what is the negative relief or the effect of the negative elevation on the relief, you will find out that it is inward in the radial line. So, that is the idea here about the relief displacement. So, let us measure length of a line on a tilted photograph. So, what does it mean? We are trying to measure the length of the line on the ground surface using tilted photograph. That means, I am going to measure the image points on the tilted photograph. I know the scale of tilted photograph that I already determined. So, then I am finding out what could be the distance between the 2 points which I do not want to measure in the field, rather I am measuring from the photograph itself. Let us look into this thing. So, this is tilted photograph and I can see the triangle here shown by red color. M dash A is in the horizontal plane and tilted photograph is this. So, I have a plane like this and there is a tilted photograph like this. So, in this horizontal plane I am defining triangle M dash M A as we did it in the previous slide also. SH is equal to AM by AM. You can see now we are defining the scale of the tilted photograph here. So, AM is this distance in the red triangle. AM is equal to x dash perpendicular to the principal line which is y dash in the photograph. So, I can write that AM which is x coordinate here in this x and y axis system. This is my y axis. So, AM is this point to this point, this measurement capital X, I am writing it here and that is x dash divided by SH and given by this. You can refer the previous slide for the final expression. Okay. What is the y distance? But now this time I am using M dash M which is measured parallel to the principal line, right. So, I can write M dash M is equal to this and NM is the y distance which is here and that is this distance. So, that is y distance I am measuring along the y axis and so it is y dash cos t divided by SH and then I can write the values of SH and here H minus. So, I am putting the value of scale only. So, because of the inversion it is coming this one and scale is same, this is scale SH. I am putting here also, I am putting here also. Now, I can say that what is the distance here for 2 points? Let us say you measure x, this distance for 1 point and y also for 1 point. Similarly, you also measure for point B and then you can find out the length on the ground surface is equal to this distance. Let us look into the tilt distortion. Because of the tilt distortion, what will happen? Image is appearing like that, not the rectangle one. So, this is a tilted photograph. Say this is the plane of tilt. So, this plane of tilt is this on the planimetric image. O is the exposure center and this is another point. So, this is a image of the another point here. There is a K point and this is a tilt angle. There are 2 points A and B on the tilted image. They are appearing at the extreme of the image. This is isocenter I here, this point. If I draw the vertical photograph, which should be correct one, so this is a vertical photograph. It is the plane of the vertical photograph indicated by this line. This is optical axis here and this is the plumb line from the exposure station. So, plumb line is intersecting the vertical photograph at N dash, but it is intersecting at N for the tilted photograph as you can see here. Now, I am connecting the exposure station with the point A and B on the tilted plane. Point A dash and B dash are the image if we have taken the vertical photograph. In fact, we are trying to derive what is the distortion. That means, if photograph was vertical, I could have got A dash B dash, but now real points are A, B on the tilted photograph and I want to find out what is the distortion from point A dash and B dash. So, this is A dash and B dash. So, let us see these angles are alpha and beta. So, I want to tilt tilted photograph such that it will match with the vertical photograph and that will give an idea that if this is point A and it is going to make point A double dash, I already know what is point A dash. So, this point is going to make A double dash So, this will be the distortion in point A. Similarly, I can find out distortion in point B also on the image. So, let us rotate the tilted plane to match with the vertical plane, or match the tilted photograph with the vertical photograph like this. Because of the rotation, the distance from point I to B is equal to I. So, this distance A dash A is equal to dA, that is the tilt distortion in point A. This is this distortion you can see here, and it is equal to the IA dash, I to A dash, right, minus I A dash. This is point A double dash and this is A dash. Similarly, I can write for point B. So, B dash B is the tilt distortion in the point B, and I can write it IB minus IB dash here. Here I have written IB dash and IB straight away. Instead of IB, I can write IB double dash also, the way I have written here. Because of the rotation, this distance IB is equal to IB double dash. We have not projected the point B onto the vertical photograph, rather we have rotated it. So, it is kind of this effect. So, if I have a radius R here, if I rotate by some angle, then it will again go here and this point will go here and a circular arc. So, this distance is R and it is also R. So, the same thing I am doing here. So, now I can see that if I join these points, so these lines are intersecting at I and they are intersecting here as well as here and so on. So, that is the concept of the tilt distortion. These two amounts are tilt distortions. Now, let us try to find out mathematically what is the amount of tilt distortion. This is focal length in the tilted plane and this is also equal to the focal length in the vertical photograph. Tilt distortion dA in the photograph. So, I can write it like this. I can also write it like this. You can see here that IA dash is equal to this one. You can see here IA dash is equal to N dash A dash minus N dash I, and I can write it F tangent T plus alpha and minus F tangent T by 2. I determined this quantity. Now, I want to find out this quantity IA. So, IA is equal to Ka plus Ki, that means this is Ka and plus Ki, these two distances shown by the dark color here, and it is equal to F tangent alpha and F tangent T by 2. So, you can use these triangles and find out. Now, I can straight away derive this term here, what is the tilt distortion for point A, which is lying below or above the tilted photograph. You can imagine, I can write this expression. So, what about point B? Again, this is focal length F. You can see here that because of the tilt distortion, point A is shifting inside like this, but point B is shifting outside because we have rotated the tilted image into the vertical image. So, I can write dB is equal to IB minus IB dash, and IB dash itself is equal to N dash B dash plus N dash I from this simple relationship of the vertical photograph. IB is equal to KB minus KI and equal to F tangent beta minus F tangent T by 2. I can write dB is equal to F tangent beta minus this distance, where tangent alpha is Ka by F. Similarly, tangent beta is not Kb divided by F. So, Kb, this distance divided by F. This is the F distance here, focal length. So, I can find out tangent beta also, tangent alpha also, focal length is known, tilt is known. I can find out what is the dB or the tilt distortion of point B. So, you can find out for any point, and that is why we have taken 2 points. One is below the photograph and one is above the photograph. That means, this point B is below the vertical photograph and this point A is above the vertical photograph in the tilted plane. Let us look into the relief distortion on the tilted photograph. Point A here, this nadir point here, A0 I can say. So, let us see A0. I am drawing some animations, you can see very carefully, they are very easy to understand. Now, this is the situation here. That is a R0 distance from isocenter to the B0. That means, this is the B0 here and this is the B point and this is the height HB here. This distance is R. This equation is still applicable if I measure the R and R0 from nadir point and not the principal point. So, I can write this expression also. So, finally, the radial displacement of a tilted photograph is radial from the nadir point and not the principal point, that you should remember, and this depends on these factors, right, r and r0 here, small h, let's put the principal line and the, so that is x dash and y dash. So, here we finish this lecture on the vertical photogrammetry. Today we have find out the height from a vertical photograph or tilted photograph. In the next lecture, we will talk about the stereo photogrammetry, that is the principle of creating 3D from multiple images. Till then, thank you.